There is a place beyond Neptune where the sun becomes a star, not a metaphor, not a poetic license, a literal optical fact. Stand far enough out in our solar system, roughly 40 astronomical units from Earth, give or take a few, depending on where Neptune sits in its orbit, and the object we call the Sun shrinks to a point of light indistinguishable to the naked eye from the other bright stars around it. You could cover it with your thumbnail. You could lose it if you looked away for too long. Most people will never experience that. Most people spend their entire lives inside a thin atmospheric shell wrapped around a single warm rock, never travelling further from their home planet than a few 100 kilometers of altitude. And the furthest any human being has ever travelled from Earth was roughly 400,000 kilometers, the distance to the Moon achieved by the Apollo astronauts. That sounds enormous until you compare it to the distance from Earth to Neptune, which is roughly 4.5 billion kilometers. The Apollo astronauts, the furthest travelled humans in history, made it approximately 1/10,000th of the way to Neptune. And Neptune is not even the edge. But here is the question this video is going to sit with for the next 2 hours. Not how far is it? Not what's out there. Those are the wrong questions. The right question, the one that changes how you feel about the dark, is this. If you were stranded out there beyond Neptune in the cold and the silence and the dark, how long would you actually survive? Not in a spacecraft with full life support. Not with a rescue mission already en route. Stranded, alone, with whatever you have, with whatever physics gives you and whatever physics takes away. The answer is not what you expect, because the threats out there don't come from the things most people imagine. They don't come from alien predators or explosive decompression or any of the dramatic deaths that science fiction has trained us to picture. The threats are quieter, more patient, more absolute, and they arrive in a very specific order, each one following the last like the ticks of a clock you cannot stop. This is that clock. Let's start with what beyond Neptune actually means, because it matters more than it might seem. Neptune orbits the Sun at an average distance of about 30 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, roughly 150 million kilometers. So Neptune sits at about 4.5 billion kilometers out. Light, travelling at 300,000 kilometers per second, takes roughly 4 hours to reach Neptune from the Sun. When you look at Neptune through a telescope, you are seeing it as it was 4 hours ago. That 4-hour lag is already disorienting if you think about it too hard, because we're used to light being effectively instantaneous. The Moon's light reaches us in about 1.3 seconds. The Sun's light takes 8 minutes, but Neptune is 4 hours away and we're not even close to the edge yet. Beyond Neptune begins the Kuiper Belt, a vast disk of icy bodies, dwarf planets, and debris extending from about 30 to 50 astronomical units. Pluto lives here. So does Eris, Makemake, Haumea. The Kuiper Belt is not empty, but it is not crowded either. It is diffuse in a way that makes the asteroid belt between Mars and Jupiter look like a traffic jam. The average distance between objects in the Kuiper Belt is enormous. You could pass through it and never see another object with the naked eye. Beyond the Kuiper Belt is the scattered disk, a region of objects with highly elliptical orbits, disturbed long ago by Neptune's gravitational influence. And beyond that, beginning somewhere around 2,000 astronomical units and extending perhaps as far as 100,000, is the Oort cloud, the vast spherical shell of icy bodies that represents the outermost gravitational boundary of our solar system. No spacecraft has ever reached it. Voyager 1, our furthest travelled human-made object, launched in 1977, travelling at roughly 17 kilometers per second, will not reach the inner edge of the Oort cloud for another 300 years. So when we say beyond Neptune, we mean a volume of space so large that it contains multitudes. And the specific location where you are stranded matters because the physics changes depending on exactly where you are. For the purposes of this thought experiment, let's place you in the Kuiper Belt, roughly 40 astronomical units from the Sun, far enough that the Sun is a bright star rather than a disk, close enough that you're still technically within the solar system's recognizable structure. This is the most plausible location for a near-future stranding scenario. If humanity ever sends crewed missions to the outer solar system, the Kuiper Belt is the first truly alien frontier they would face. You are there, right now, in whatever you're wearing, with whatever is in your pockets. The first thing that kills you out there has nothing to do with cold, nothing to do with radiation, nothing to do with any of the exotic physics of deep space. The first thing that kills you is the most ordinary, the most mundane, the most embarrassingly human thing imaginable. It is suffocation. At 40 astronomical units in the vacuum of space, you have whatever air is in your lungs at the moment of stranding. That's it. No atmosphere, no ambient oxygen, just what you brought with you in your chest when the scenario began. The human body, under normal resting conditions, can extract oxygen from a single breath for roughly 30 to 45 seconds before that breath becomes too carbon dioxide rich to sustain consciousness. Under stress, and being stranded beyond Neptune would qualify as stressful, that window shrinks. Your heart rate increases, your muscles consume more oxygen, your breathing becomes rapid and shallow, which is actually counterproductive, because it reduces the efficiency of gas exchange in your lungs. The physiology of suffocation in a vacuum is slightly different from drowning or being strangled, and the difference is important. When you hold your breath, carbon dioxide builds up in your blood, and it is the CO2 increase, not the oxygen decrease, that triggers the overwhelming urge to breathe. Your body's primary suffocation alarm is a CO2 sensor, not an O2 sensor. This means that in a vacuum, if you exhaled fully before your exposure, you'd actually feel less distress than if your lungs were full, more because there would be less CO2 to accumulate. But you would also have less oxygen, so the window would be shorter either way. The useful consciousness window for a human being in the vacuum of space, accounting for the specific physiological cascade of oxygen deprivation and CO2 buildup, is generally estimated at around 9 to 11 seconds before you lose consciousness. You don't explode. You don't freeze instantly. You don't die in a dramatic Hollywood spectacle. You have approximately 10 seconds of awareness, and then the lights go out. After that, biological death follows within 2 to 3 minutes as the brain is deprived of oxygen. The body continues to exist. Tissue death is slower and follows a predictable biological clock. But you, the conscious entity asking these questions, are gone in under a minute. 10 seconds. That is your unprotected survival time beyond Neptune. That is the baseline. Everything else in this video, every other countdown, every other timeline, every other phase of this thought experiment requires that you are protected from that immediate death first. So for the rest of this video, we are going to assume you have a spacesuit, a real one, a functional one with a closed life support system, because the interesting question is not how long the vacuum takes to kill you. The interesting question is how long everything else takes once you've solved the vacuum. A modern spacesuit, specifically the kind used for extravehicular activity on the International Space Station, known as the Extravehicular Mobility Unit, or EMU, carries a primary life support system with a nominal operational duration of about 8 hours. There is also a backup system called the secondary oxygen pack, which provides an additional 30 minutes in an emergency. So, in the best case, with a fully charged suit, you have approximately 8.5 hours of breathable air. 8.5 hours. That is your first hard deadline, your first ticking clock. But 8.5 hours is an average, it is a rated duration under standard conditions. Out beyond Neptune, conditions are not standard. And this is where the physics starts to compound in ways that are not immediately obvious. The first complication is temperature. Space as a concept is often described as cold. This is technically imprecise. Space is not cold in the way a refrigerator is cold. Cold is a property of matter. It describes the average kinetic energy of molecules. In a near-perfect vacuum, there is almost no matter, so there is almost nothing to be cold or hot. The temperature of the vacuum itself is approximately 2.7 Kelvin, the cosmic microwave background radiation, the afterglow of the Big Bang. But that temperature is effectively irrelevant to your survival because there is no medium through which it can transfer to your body at any meaningful rate. What is relevant is radiation. And at 40 astronomical units from the Sun, solar radiation, the light and heat that keeps Earth warm, is reduced to a tiny fraction of what it is on Earth. The intensity of sunlight follows an inverse square law. Double your distance from the Sun and you receive 1/4 of the light. At 40 astronomical units, you receive 1/1600th of the solar energy that Earth receives. The Sun delivers about 1,360 watts per square meter to Earth's orbit. At 40 astronomical units, it delivers less than a single watt per square meter. This matters for your suit in two ways. First, your suit is designed with thermal management in mind. On Earth orbit, astronauts face extreme temperature swings. In direct sunlight near Earth, surfaces can reach 120 degrees Celsius. In shadow, they drop to negative 150 degrees Celsius. The suit manages this with layers of insulation and a liquid cooling and ventilation garment worn next to the skin. But these thermal systems were designed for the sunlight intensity near Earth. At 40 astronomical units, your suit's solar gain is essentially zero. You are in permanent thermal shadow regardless of your orientation. The second implication, without solar energy, your suit's batteries, which power the life support system, the communications, the heating elements, become your only energy source. And batteries drain. The EMU's primary life support system runs on lithium hydroxide canisters for CO2 scrubbing and a battery pack. The battery capacity in the suit's design is sized for the operational mission duration, roughly 8 hours. If temperatures are dropping and the suit's heaters are working overtime, that drain accelerates. In the thermal environment beyond Neptune, your heaters would be running constantly, fighting a losing battle against the inexorable heat loss through radiation. This is not the same as conductive cooling. You're not touching something cold, but your suit radiates infrared energy into the void and nothing radiates it back. In practical terms, the thermal drain could reduce your effective operational time significantly. Estimates vary depending on suit design parameters, but a reasonable engineering assessment suggests that in the thermal environment of the outer solar system, The continuous heater load could cut battery life by 20 to 40%. That 8.5 hours begins to look more like 5 or 6. So let's set that as phase 1, 5 to 8.5 hours. This is the oxygen and power window. This is how long you have before the suit fails. But here is the thing about that window that changes everything. It is not a window of comfort. It is a window of increasing crisis, because the life support system does not fail all at once. It degrades. The CO2 scrubbing system, which removes carbon dioxide from the air you exhale, uses a chemical absorbent, primarily lithium hydroxide. This absorbent is not regenerative. It absorbs CO2 until it is saturated, and then it stops working. On a standard EVA timeline, the canisters are sized to last the mission duration, but the rate at which you exhale CO2 is not constant. It varies with your metabolic rate. If you are panicking, and you would be panicking, your breathing rate increases, your metabolism elevates, and you burn through the scrubbing capacity faster. Carbon dioxide poisoning, which is technically what kills you when the scrubber fails, is insidious. It doesn't feel like suffocation at first. CO2 buildup at mild concentrations causes headache, dizziness, and confusion. At moderate concentrations, you lose coordination and judgment. At high concentrations, you lose consciousness. The process can take anywhere from minutes to over an hour, depending on the rate of buildup. But the cognitive effects, the confusion and poor decision-making, arrive well before the loss of consciousness. This means that in the first phase of your stranding, the threat is not just running out of time. The threat is that you will progressively lose your ability to think clearly, precisely when clear thinking matters most. The clock is ticking, and the very mechanism that would allow you to read the clock is degrading. What could you realistically do in that window? If this were a real scenario, if we imagined a crude mission to the outer solar system that experienced a catastrophic separation event, the actions taken in that first phase would determine everything. Communication would be the priority. The suit's communication system operates on radio frequencies at 40 astronomical units. The signal would take approximately 5.5 hours to reach Earth, one way. That means a distress call sent in the first minute would not even arrive at Earth until you were already dead, or nearly so. And a response from Earth would not reach you for another 5.5 hours after that. You are 11 hours of signal delay away from a conversation. 11 hours. Your suit lasts 5 to 8. This is the first truly existential number in this video, not because it is the largest, the timelines ahead of us dwarf it completely, but because it is the first number that locks in the outcome. At 40 astronomical units from Earth, real-time communication is physically impossible. Not technologically limited, not a solvable engineering problem, physically impossible because of the speed of light. The universe has a speed limit, and it makes rescue at that distance a mathematical impossibility on any human timescale. Let's let that land for a moment. The 5 to 8 hour life support window is not a tragedy caused by technological limitations. It is not a problem that better engineering could have prevented. Even if we designed a suit that lasted 24 hours or 72 hours or a week, the signal delay remains. The light speed barrier remains. Anyone trying to help you would be operating on information that was already hours old by the time they received it. Any instruction they sent back would arrive hours after they sent it. The physics of communication at interstellar distance makes coordinated rescue effectively impossible. But here is where the thought experiment gets deeper, because survival is not always about rescue. Sometimes it is about extension. About buying time, not because rescue is coming, but because more time means more options. More time means the physics of your situation continues to evolve in ways that might open windows that a 5-hour window cannot. What happens to you physically over that first phase? The cold is the constant companion. Even inside a functioning suit, thermal management is difficult in the outer solar system. The heating system fights to keep your core temperature in the 36 to 37 degrees Celsius range. If it fails, or if it is operating at partial capacity, hypothermia begins. The human body loses heat gradually in an environment where conductive and convective loss is eliminated, as it is in a spacesuit, but radiative loss continues. Your suit's outer layers radiate heat to the cold of space. Without adequate countermeasures, core body temperature can begin dropping within hours. Mild hypothermia begins around 35 degrees Celsius. Shivering starts. Cognitive function remains largely intact, but fine motor skills begin to degrade. This is relevant because operating suit systems, adjusting controls, and performing any kind of emergency procedure requires fine motor skills. Moderate hypothermia begins around 32 degrees Celsius. Shivering may paradoxically stop as the body's heat-generating capacity becomes exhausted. Confusion sets in, coordination fails. The person experiencing this typically does not recognize that they are impaired. Severe hypothermia begins around 28 degrees Celsius. Loss of consciousness, cardiac arrhythmia. At this stage, without external intervention, death is likely within hours. Now layer this on top of the CO2 buildup from the degrading scrubber, and you begin to see the compound nature of the crisis. The first phase is not a single problem. It is a convergence of problems. Oxygen, CO2, power, heat, all on slightly different timescales, all interacting with each other, all contributing to a degrading situation in which your ability to respond degrades faster than the situation itself. The clock in phase 1 does not tick at a constant rate. It accelerates. There is one more factor in phase 1 that is rarely discussed, but is physiologically significant: psychological stress and its metabolic consequences. Fear elevates cortisol. Cortisol elevates blood glucose. Elevated blood glucose increases metabolic rate. Increased metabolic rate increases oxygen consumption. The increased oxygen consumption accelerates the depletion of life support resources. This is not a minor effect. Studies of astronaut physiology during high-stress operational periods show metabolic rates 20 to 30% above baseline. In a survival scenario, genuinely stranded, genuinely alone, with no real prospect of rescue, psychological stress would almost certainly be extreme and sustained. That 20 to 30% metabolic increase could realistically shave another hour off your effective life support duration. So the honest, physiologically grounded answer to phase 1 is this: with a fully charged, fully functional spacesuit deployed in the thermal environment of the Kuiper Belt, accounting for accelerated CO2 scrubber depletion from elevated metabolism, accounting for increased heater load from near-zero solar gain, and accounting for the psychological stress of a genuine survival crisis, your realistic life support window is somewhere between 4 and 7 hours. 4 hours on the low end, 7 on the high, and within that window communications with Earth are impossible in any real-time sense. A distress call would arrive at Earth after the window has already closed. You would be gone before anyone on Earth even knew you needed help. That is phase 1. That is the first clock. But this video is not about 4 to 7 hours. It is about what happens after, to your body, to your equipment, to the physics of your situation. If by some mechanism, through some imaginable technology, the life support problem is solved, if we extend the window, if we ask, what is the next thing that kills you and how long does that one take? Because the answer to that question changes everything. It reveals a landscape of nested countdowns, each one longer than the last, each one more alien, more patient, more absolute. The universe, it turns out, is not in a hurry, but it is thorough, beyond the oxygen window, beyond the thermal crisis, beyond the CO2 buildup and the battery drain, and the psychological disintegration of a human mind staring into the Kuiper Belt at 4 a.m. Of the soul, there are other clocks running, slower clocks, clocks that were ticking before you arrived and will tick long after. And understanding them changes how you see the dark. Let's say you survive phase 1. Not because the physics changed, not because the suit lasted longer than it should have, but because we're going to do something that science fiction has always done, and that serious thought experiments require. We are going to grant you a technology, not an impossible one, not a hand wave, a plausible one, the kind that engineers at NASA and ESA actually discuss when they talk about long-duration deep space missions. We are going to give you a closed-loop life support habitat. Think of it as a very small pressurized module, perhaps the size of a large SUV, perhaps the size of a shipping container. It doesn't matter exactly. What matters is that it has a power source, a CO2 scrubbing system that is regenerative rather than expendable, a water recycling system, a thermal management system, and enough stored food and consumables to extend your survival window from hours to something longer. This is not fantasy. The International Space Station is essentially this, scaled up. The life support systems aboard the ISS are closed-loop to a significant degree. They recycle water from urine condensation and humidity. They generate oxygen through electrolysis of water. They scrub CO2 using a system that regenerates the absorbent rather than exhausting it. The technology exists. It has been tested in continuous operation for over 2 decades. So you have that. A small habitat, a lifeboat, effectively. And now the question becomes, what is the next clock, and when does it run out? The first thing to understand about extended survival beyond Neptune is that you are no longer fighting the immediate crisis of vacuum and cold. You have bought time. But buying time in the outer solar system means entering into a much longer negotiation with a set of threats that are less dramatic and more insidious than suffocation. The first of these threats, the one that begins accumulating the moment you are stranded, regardless of what equipment you have, is radiation. Not the radiation most people think of when they hear the word, not the immediate acute radiation of a nuclear weapon or a reactor breach. That kind of radiation would kill you in hours or days through direct cellular destruction, and it is not the primary radiation threat in the outer solar system. The radiation threat beyond Neptune is slower, quieter, and cumulative. It is the constant background rain of high-energy particles that fills the space between the stars. To understand it properly, you need to understand where it comes from. There are 2 primary sources of radiation in the outer solar system: solar energetic particles, which are high-energy protons, and electrons ejected by the Sun during solar events, and galactic cosmic rays, which are high-energy particles, primarily protons, but also heavier atomic nuclei that originate from outside our solar system, from supernova explosions and other high-energy astrophysical events across the galaxy. Near Earth, we are protected from much of this radiation by two mechanisms. The first is the geomagnetic field. Earth's magnetic field deflects a significant fraction of charged particles, channeling them toward the poles where they produce the aurora rather than raining down on populated latitudes. The second is Earth's atmosphere, which provides roughly 10 meters of water-equivalent shielding. When a cosmic ray particle hits the upper atmosphere, it triggers a cascade of secondary particles, and by the time that cascade reaches sea level, the original particle's energy has been distributed and reduced to largely harmless levels. In deep space, you have neither of these protections. You are exposed to the full, unshielded flux of galactic cosmic rays 24 hours a day. Every day you are out there. The dose rate from galactic cosmic rays in deep space, measured by instruments aboard missions like Curiosity on its journey to Mars, is roughly 1.8 millisieverts per day. For context, the annual radiation dose limit for radiation workers in the United States is 50 millisieverts per year. The career limit for NASA astronauts is set at a level calculated to represent no more than a 3% increase in lifetime cancer risk, which works out to roughly 600 to 1,200 millisieverts depending on age and sex. At one point, 8 millisieverts per day, you reach the annual radiation worker limit in about 28 days. You reach the lower end of NASA's career limit in about a year, but here is the complication that changes the math in the outer solar system specifically. The Sun is not just a source of radiation, it is also a shield. The solar wind, the constant stream of charged particles that flows outward from the Sun at roughly 400 kilometers per second, creates a bubble called the heliosphere that extends through the entire solar system and slightly beyond. This bubble acts as a partial deflector for galactic cosmic rays. The pressure of the solar wind and the interplanetary magnetic field it carries push against the incoming flux of cosmic rays, reducing the dose rate inside the heliosphere compared to what you would receive in interstellar space. At Earth's orbit, this shielding effect is significant. Closer to the Sun, you receive less galactic cosmic radiation. Further from the Sun, as the solar wind weakens and the heliospheric bubble thins, you receive more. At 40 astronomical units, the Kuiper Belt, the heliospheric shielding is substantially reduced compared to Earth orbit. Measurements from the Voyager probes, which crossed the boundary of the heliosphere at around 120 astronomical units, showed a sharp increase in cosmic ray flux at and beyond the heliopause. What this means for your survival scenario: your daily radiation dose beyond Neptune is higher than the 1.8 millisieverts per day measured near Earth's orbit. Current models suggest dose rates in the outer heliosphere could be 20 to 30% higher than in the inner solar system. Call it 2.2 to 2.4 millisieverts per day. At 2.3 millisieverts per day, you accumulate 50 millisieverts in about 22 days. You accumulate 600 millisieverts, the lower NASA career limit, in about 260 days, less than 9 months. But radiation does not work like a simple on-off switch. The damage is probabilistic and cumulative. Below certain thresholds, the body's DNA repair mechanisms handle most of the damage adequately. Above those thresholds, the repair mechanisms are overwhelmed, and the probability of unrepaired damage, which can manifest as cancer, increases. The cancer is not immediate. The latency period for radiation-induced cancers is typically 5 to 30 years after exposure. But the biological damage accumulates in real time. Practical implication for your habitat: shielding matters enormously. Water is an excellent radiation shield. It absorbs and scatters high-energy particles effectively. A habitat with walls of water storage, water you need for life support anyway, provides meaningful shielding. Polyethylene, which is rich in hydrogen atoms that interact efficiently with cosmic ray particles, is even better per unit mass. NASA has studied polyethylene-based shielding for deep space habitats extensively. With adequate shielding, say warm coal, the equivalent of 20 to 30 grams of water per square centimetre, you can reduce your daily effective dose to perhaps a third of the unshielded value. Call it 0.7 to 0.8 millisieverts per day. That brings your timeline to the NASA career limit out to roughly 2 years rather than 9 months. 2 years. That is your extended survival window from a radiation standpoint, defined as the point at which your cumulative exposure represents a meaningfully elevated cancer risk. Not death, not immediate incapacitation, just a clock that is running silently and invisibly in the walls of every cell in your body. The second extended threat is bone and muscle loss. This one is less exotic but no less serious. Microgravity, or more precisely, the absence of gravitational loading, causes the human body to begin cannibalizing its own structural support systems almost immediately. The mechanism is straightforward. Bones and muscles are maintained by the body's continuous response to mechanical loading. In a gravitational environment, every step you take, every movement you make, loads your skeleton and triggers the biological processes that keep bone density high and muscle mass intact. In microgravity, those loading signals disappear. The body, ever efficient, interprets the absence of loading as an absence of need. Bone-building cells reduce their activity. Bone-resorbing cells continue theirs. The net result is bone mineral density loss at a rate of roughly 1 to 2% per month in the load-bearing bones, spine, hips, femur. 6 months of microgravity exposure can cause bone density losses, equivalent to a decade of normal aging on Earth. For astronauts on the ISS, this is managed through a rigorous exercise regimen, 2 hours of vigorous exercise per day, using specially designed resistance and aerobic machines that simulate gravitational loading. This regimen reduces but does not eliminate bone loss. Studies of long-duration ISS crew members show residual bone density losses of 0.5 to 1% per month, even with the exercise protocol. In your survival habitat, with limited equipment and potentially limited energy resources for powering exercise machines, the bone loss rate could be at the higher end. At 2% per month, you lose 20% of your load-bearing bone density in 10 months. At that level of loss, we fracture risk under any return to gravitational environment if you were somehow rescued and returned to Earth would be extreme. Your bones, after a year in microgravity, would be comparable in density to those of a person with severe osteoporosis. Muscle loss follows a similar but faster trajectory. Skeletal muscle, the type that moves your body, begins atrophying within days of microgravity exposure. Without exercise countermeasures, you can lose 20% of your muscle mass in the first 5 to 11 days. Beyond that, the rate slows somewhat but continues. Over months to years, the loss is profound. The heart is also a muscle, and it is not exempt. In microgravity, the cardiovascular system adapts to not working against gravity. Blood no longer pools in the legs, and the heart reduces its output accordingly. This cardiovascular deconditioning means that if you were returned to a gravitational environment, your heart would be working significantly harder than it was designed to work given its deconditioned state. These two threats, radiation and physiological deconditioning, define the extended survival timeline in a way that the immediate oxygen crisis does not. They are not instant killers, they are slow erasers. They work on the body like time works on stone, incrementally, invisibly, and with increasing consequence. Now, let's add the third threat in the extended window. This one is the strangest, the most alien, the hardest to prepare for. It is isolation, not in the colloquial sense of being lonely. In the clinical, neurological sense of what happens to the human brain when it is deprived of the environmental complexity and social interaction it evolved to require. The human brain is a prediction machine. It is constantly building and revising models of the world based on sensory input. It anticipates, it contextualizes, it finds pattern in chaos and story in randomness, and it does all of this in the context of an environment that, throughout the entire evolutionary history of our species, was rich with variation, weather, terrain, other people, unexpected events, the constantly changing texture of the natural world. Beyond Neptune, the visual environment is a black sky with a bright star where the sun used to be, and a scattering of other stars that do not move on any human time scale. The sounds are whatever your habitat makes, mechanical hums, your recycling system gurgles, your own breathing. There is no weather, no terrain, no wildlife, no seasons in any perceptible sense. The stars do not change. The dark does not change. The silence does not change. Psychological studies of extreme isolation, in Antarctic winter overstations, in submarine deployments, in simulated Mars missions like the HISEAS studies in Hawaii, consistently show a predictable sequence of psychological deterioration in environments that are prolonged, confined, and monotonous. In the first weeks, there is typically heightened anxiety and difficulty sleeping. The brain is still running on its normal threat response systems, still expecting that the situation will change, still bracing for something to happen. When nothing happens, when the dark continues to be dark and the silence continues to be silent, the anxiety gives way to something quieter and more dangerous. Depression, cognitive blunting, a gradual flattening of emotional response, and intellectual engagement. The brain, no longer receiving the environmental novelty it needs to stay calibrated, begins to reduce its own sensitivity. Colors seem less vivid, ideas feel less interesting, the motivation to perform maintenance tasks, critical survival tasks, erodes. Beyond roughly 3 months of extreme isolation, a phenomenon called cognitive tunneling can emerge. The person's attention narrows to immediate, low-complexity tasks and struggles to engage with anything requiring sustained abstract reasoning. A long-term planning, which would be essential for maximizing survival duration, becomes progressively harder. Beyond 6 months, the most consistent finding in isolation research is what Antarctic researchers call the third quarter phenomenon. A sharp increase in psychological dysfunction around the three-quarter point of a known isolation period, characterized by irritability, social withdrawal, difficulty concentrating, and a sense of purposelessness. The third quarter phenomenon appears even in isolation studies where the end date is known and rescue is certain. In your scenario, where no end date is known and rescue is not coming, the psychological deterioration would be unanchored to any recovery expectation. The brain, deprived of social contact, does something else that is less discussed but well documented. It generates social experience internally. Isolated individuals consistently report developing intense emotional relationships with objects, with abstract concepts, with the sensory memories of people they knew. This is not madness. It is the brain's adaptive attempt to satisfy social needs when no external social input is available, but it consumes cognitive resources, and over time, it can make it increasingly difficult to distinguish between internal experience and external reality. In the context of your survival timeline, the psychological deterioration represents a threat that is not on a fixed clock in the way that radiation or bone loss is. It interacts with the other threats, amplifying them. Depression increases the cortisol load, which increases inflammation, which accelerates bone loss and impairs immune function. Cognitive tunneling impairs the maintenance and monitoring of life support systems. The loss of motivation undermines the exercise regimen that is slowing bone loss. The threats are not independent variables. They are a system, and they drive each other. There is one more element to Phase 2 that changes the nature of the survival problem in a way that almost nothing else does, and it has to do with the particular property of the outer solar system that makes it unlike anywhere else human beings have ever been or are likely to go for a very long time: the light. At 40 astronomical units, the Sun delivers less than 1 watt per square meter. This is not enough for photosynthesis. It is not enough for most solar power applications. It is effectively starlight, brighter than any other star in the sky by a significant factor, but orders of magnitude dimmer than the Sun as experienced on Earth or even in low Earth orbit. This matters for survival in 2 ways. The first is practical. Solar power, which is the primary energy source for spacecraft within the inner solar system, is not viable in the Kuiper Belt. The power density is too low. A solar panel array that generates useful power near Earth would need to be hundreds of times larger to generate the same power beyond Neptune. And hundreds of times larger means hundreds of times more mass, more cost, more engineering complexity. Power in the outer solar system means nuclear power, radioisotope thermoelectric generators, or RTGs, like those that power the Voyager probes and the New Horizons mission, or, in near-future scenarios, compact nuclear fission reactors. If your habitat has an RTG, your power situation is stable for years to decades. RTGs produce power continuously through the radioactive decay of their fuel, typically plutonium-238, with a half-life of about 87 years. They cannot be turned off, they do not require fuel resupply, and they are extraordinarily reliable. If your habitat has a solar power system designed for inner solar system use, your power situation is an emergency from the first moment. The second way that light matters is biological. The human circadian rhythm, the internal 24-hour clock that governs sleep, hormone cycles, metabolism, and cognition, is entrained primarily by light, specifically by the cycle of light and dark. In the complete absence of natural light variation, which is the permanent condition beyond Neptune, the circadian system begins to drift. Sleep becomes fragmented. Hormone cycles desynchronize from each other. Metabolism fluctuates unpredictably. Research on people living and working in polar regions during winter, where sunlight disappears for months, consistently shows disrupted sleep architecture, increased depression and anxiety, reduced cognitive performance, and altered immune function. These effects compound the isolation psychology described earlier. Your body's internal clock, in the permanent dark beyond Neptune, would have nothing to synchronize to except your own artificial lighting schedule. And maintaining a rigorous artificial lighting schedule requires exactly the kind of disciplined routine that becomes progressively harder to maintain as psychological deterioration advances. This is the recursive trap of long-duration survival in the outer solar system. The threats undermine the behaviors that would slow the threats. So where does Phase 2 leave us? If we grant the habitat, the closed-loop life support, the nuclear power source, and the food supply, all plausible near-future technologies, your survival timeline in the outer solar system extends dramatically past the original 4 to 7 hours. But it is bounded. The radiation clock is running at a dose rate that, without adequate shielding, crosses meaningful risk thresholds within months. With good shielding, it extends to years. Bone and muscle loss is manageable with exercise, but not indefinitely. The countermeasures buy time, they do not stop the clock. Psychological deterioration progresses on a schedule that is not fully controllable by any individual, no matter how psychologically robust. A realistic outer bound for Phase 2, granting all the technological benefits, is somewhere between 3 and 5 years before the compound effects of radiation, physiological deconditioning, and psychological deterioration would make continued biological function effectively impossible, even if the immediate survival needs of air, water, food, and warmth continued to be met. 3 to 5 years. From 4 to 7 hours to 3 to 5 years. That is the distance that technology buys you. That is the gap between immediate death and slow unraveling. But there are longer clocks. There are always longer clocks, because beyond Neptune, after the human timescales have been exhausted, after the biology has run its course and the machines have finally run out of power and the last warmth has radiated away into the dark, the physics continues. And the physics, out there, does things to matter and time and space that make everything we have talked about so far look like a footnote. The next clock starts after you are gone, and it runs for a very long time. You are gone now. Let's be precise about what that means, because precision matters when we are about to talk about timescales that dwarf human comprehension. You, the conscious, experiencing entity that began this thought experiment stranded beyond Neptune, ceased to exist somewhere in the 3 to 5 year window of Phase 2. The brain stopped. The heart stopped. The biological processes that constitute a living human being wound down in the cold interior of a habitat that had, by then, likely exhausted some critical consumable or crossed some threshold of system degradation from which recovery was impossible. But your body is still there, and your equipment is still there, and the Kuiper Belt, indifferent and patient and ancient, continues to do what it has been doing for 4.5 billion years. This is where the thought experiment changes character entirely. We are no longer asking how long you survive. We are asking what survives of you, and for how long, and what the universe does with the remnants of a human being and a human-made machine left alone in the outer solar system. The answers are stranger than you might expect, and they connect, in ways that are not immediately obvious, to the deepest questions about the long-term fate of matter itself. Let's start with the body. On Earth, a human body decomposes through a well-understood biological process driven primarily by bacteria, both the bacteria that live in the gut and colonize the body from the moment of death, and the bacteria and fungi in the surrounding environment. Decomposition under normal terrestrial conditions is rapid. An unprotected body in a temperate climate can be reduced to skeletal remains within weeks to months depending on temperature, humidity, insect activity, and scavenging. The chemistry is driven by enzymatic breakdown of soft tissue, followed by bacterial fermentation, followed by the slower processes of adipocere formation or mummification under certain conditions. None of this applies beyond Neptune. In the vacuum, in the cold, in the absence of liquid water and the near absence of any biological activity, decomposition, as we understand it, essentially stops. The body does not rot. It does not decay in the biological sense. It undergoes a different process, one that is slower by orders of magnitude and driven by physics rather than biology. The first process is desiccation. In a vacuum, water sublimates. It transitions directly from solid ice to water vapor without passing through a liquid phase. Any remaining moisture in the body, if exposed to vacuum, would sublimate away relatively quickly. Inside a sealed habitat, the situation is different. The water stays. But eventually, as the habitat loses integrity, or as we imagine the scenario extending long enough for the habitat to fail, the body encounters vacuum conditions. A body exposed to vacuum in the temperature environment of the Kuiper Belt, roughly 40 to 50 Kelvin, or about negative 220 to negative 230 degrees Celsius, would freeze rapidly. Not instantly. The thermal mass of a human body is significant, and heat loss in a vacuum is purely radiative, which is slower than conductive cooling. But over hours to days, the body would reach thermal equilibrium with its environment. At those temperatures, virtually all chemical reactions stop. Enzymatic activity, which drives biological decomposition, requires liquid water and temperatures in the range where biological molecules remain flexible. At 40 Kelvin, water is not liquid. It is not even ordinary ice. It is a rigid, amorphous solid, locked into a glassy state that does not flow or react under normal conditions. Organic molecules at those temperatures have essentially no thermal energy to drive chemical reactions. What you are left with, after the desiccation and the freezing, is a cryogenically preserved human body. Not deliberately preserved in the way that cryonics companies preserve clients, with careful protocols to prevent ice crystal formation and cellular damage, but preserved in the sense that biological decomposition has been essentially arrested. How long does this preservation last? In the absence of other processes, a very long time. The chemical stability of frozen organic matter in the outer solar system is well attested. We know from the study of cometary material and Kuiper Belt objects that organic molecules can persist in the frozen outer solar system for billions of years. The amino acids and complex organic molecules found in primitive meteorites, which originated in the outer solar system, are billions of years old and still chemically recognizable. The deep cold and the vacuum are extraordinarily effective preservatives. But there is one process that does work on frozen organic matter in the outer solar system, even at those temperatures, even in the cold and the dark. It is radiation. The same galactic cosmic rays that were threatening your cells while you were alive continue to rain down on the frozen remnants of your body after you are gone. And at the molecular level, they do something interesting. High-energy particles passing through frozen organic matter break chemical bonds. They fragment molecules. They create reactive fragments that, even at low temperatures, can recombine in new configurations. Over very long timescales, this process, called radiation chemistry or radiolysis, chemically alters the composition of irradiated organic material. The reddish coloration of many Kuiper Belt objects, the reason Pluto has that distinctive reddish-brown tholins on its surface, is believed to be the product of exactly this process. Simple organic molecules irradiated over billions of years polymerize into complex reddish macromolecules called tholins. The surface of Pluto, in a very real sense, is the product of billions of years of cosmic ray chemistry operating on frozen methane and nitrogen ice. Your body, over long enough timescales, would undergo a similar process. Not rapidly. The timescale for significant radiolytic alteration of organic material in the outer solar system is estimated at millions to tens of millions of years. But it would happen. The complex organic molecules that constitute a human body, the proteins, the lipids, the nucleic acids, would gradually be broken down and recombined into simpler and then progressively more complex radiolytic products. Over millions of years, the chemical signature of a human being would blur and then disappear into the background chemistry of the outer solar system. There is something both humbling and beautiful about this, if you allow yourself to sit with it. The atoms of your body are not destroyed. Carbon, hydrogen, oxygen, nitrogen, phosphorus, they don't go anywhere. They are redistributed into new molecular configurations, incorporated into the chemistry of the Kuiper Belt, mixed over millions of years of gentle orbital dynamics with the rest of the frozen material of the outer solar system. In a very long time, the atoms that were once you become indistinguishable from the primordial material of the solar system. The same stuff from which the planets formed, the same ice and carbon that drifts in the dark between Neptune and the stars. You become part of what was already there. Now, let's turn to the equipment, the habitat, the machines, the metal and polymer and glass and ceramic of human engineering left in the Kuiper Belt. Metal behaves very differently from organic matter in this environment. The primary threat to metals in a space environment is corrosion, and corrosion requires an oxidizing agent and typically liquid water. Now, in the vacuum of the Kuiper Belt, at temperatures far below the point where any corrosive chemistry could operate, metallic structures are extraordinarily stable. Aluminum, titanium, stainless steel, the typical structural materials of spacecraft, would remain physically intact for timescales that are genuinely difficult to comprehend. There is, however, a slow process that does affect metal structures over very long timescales in space. It is called micrometeorite erosion. And it is exactly what it sounds like. The outer solar system is not completely empty. It contains a diffuse population of dust particles and micrometeorites, tiny fragments of rock and ice that orbit the Sun on their own trajectories and occasionally collide with other objects. In the inner solar system, this flux is higher. In the outer solar system, it is lower but non-zero. Over millions of years, the cumulative impact of micrometeorites on a metallic surface does cause measurable erosion. The rate is slow, estimated at roughly 1 millimeter of erosion per 100 million years for exposed metal in the outer solar system. But over geological timescales, it adds up. A habitat with walls a few centimeters thick would be significantly eroded over hundreds of millions of years and effectively destroyed over billions. There is also thermal cycling to consider, though in the outer solar system it is far less severe than in Earth orbit. With essentially no solar variation at 40 astronomical units, the thermal environment is remarkably stable. The temperature, barely changes. This actually means less thermal cycling stress on materials than in inner solar system environments, which is another factor that extends the structural lifetime of your habitat. Let's put some numbers on this. Your habitat, made of modern aerospace-grade aluminum and titanium alloys in the vacuum and cold of the Kuiper Belt, would remain structurally recognizably manufactured, recognizably artificial for somewhere between 100 million and 1 billion years. The exact timescale depends on the micrometeorite flux, the specific materials, the original wall thickness, and the presence of any additional erosion mechanisms. But the order of magnitude is hundreds of millions to billions of years. To put that in context, the age of the entire solar system is 4.5 billion years. The age of the Earth is 4.5 billion years. The dinosaurs went extinct 66 million years ago. Your habitat, abandoned in the Kuiper Belt today, would still be identifiable as an artificial object, a manufactured thing shaped by intelligence, long after the geological record of every dinosaur that ever lived has been completely erased by tectonic processes on Earth. This is not a metaphor. It is the actual physics-derived answer to the question of what survives of you in the outer solar system. The outer solar system is, in a profound sense, a museum. Unlike the inner solar system, where active geology, atmospheric weathering, biological activity, and volcanic resurfacing continuously destroy and overwrite the record of the past, the outer solar system is geologically inert. The Kuiper Belt objects we observe today look essentially the same as they did billions of years ago. Their surfaces are modified by cosmic ray radiation, but their bulk structure is unchanged. The comets that periodically visit the inner solar system are delivering material that has been frozen since the formation of the solar system, carrying molecular fossils of the chemistry that existed before the planets formed. In this museum, your habitat would be an exhibit, a timestamp, a record of a moment when a technological civilization existed on the third planet from the Sun and sent its artifacts, and perhaps its dead, to the outer darkness. Now, let's extend the timeline further, because the really interesting physics starts happening at timescales that exceed the structural lifetime of your habitat. At some point, somewhere in the range of hundreds of millions to a billion years, your habitat is no longer a habitat. It is debris, fragments, scattered material in the Kuiper Belt, its artificial geometry erased by micrometeorite impacts and perhaps by a collision with a larger Kuiper Belt object, the kind of low-velocity collision that happens on geological timescales even in the sparse outer solar system. But the atoms are still there, all of them. The carbon from your body, the aluminum and titanium from your habitat, the iron and silicon and every other element that went into building the machine that kept you alive for a few years in the dark. And now something interesting happens on a time scale of billions of years. The solar system is not static. It is dynamically evolving, and the Kuiper Belt in particular is a zone of slow, chaotic gravitational evolution. Over billions of years, gravitational interactions between Kuiper Belt objects and between those objects and the giant planets, particularly Neptune, slowly shift orbital parameters. Objects that have been in stable orbits for hundreds of millions of years can find their orbits perturbed into chaotic trajectories that eventually bring them into the inner solar system as comets, or eject them entirely from the solar system into interstellar space. The time scale for significant orbital evolution in the Kuiper Belt is measured in billions of years. But on that timescale, a substantial fraction of Kuiper Belt objects are eventually either scattered into the inner solar system or ejected. The scattered disk, the region of Kuiper Belt objects with highly eccentric orbits, is believed to be populated primarily by objects that were originally in the classical Kuiper Belt and were gravitationally scattered by Neptune over billions of years. The atoms of your body incorporated into the Kuiper Belt's frozen chemistry over millions of years of radiolysis might eventually find themselves in one of these perturbed objects, swept up in a comet nucleus that begins a long, slow journey inward toward the Sun. If that comet reaches the inner solar system, a process that takes millions to tens of millions of years after the perturbation event, it would begin to sublimate as it approaches the Sun. The frozen ices would vaporize. And the dust and organic material locked in the comet nucleus would be released into the inner solar system as a diffuse cloud of particles. Some of those particles would be swept up by planets, by the Sun, by the moons of the inner solar system. Some tiny fraction, unimaginably small, statistically vanishing, might even fall on Earth. If Earth still exists at that point, which is a question we will get to. The atoms of your body, stranded beyond Neptune, could eventually fall as cometary dust on the planet you came from. On a timescale of hundreds of millions to billions of years. This is not comfort. It is not meant to be. It is physics, but it connects the individual tragedy of being stranded, the 4 to 7 hours of suit life, the 3 to 5 years of habitat extension, either millions of years of cryogenic preservation, to something much larger. The atoms do not care about the timeline, they do not experience the billions of years between your death and their eventual redistribution through the solar system. But the story of those atoms, traced from the Kuiper Belt through gravitational perturbation and cometary delivery back to the inner solar system, is a real story. It is happening right now to material that has been in the outer solar system since before the Earth formed. You would not be the first material to make that journey. You would just be the only material that once asked how long it had. Now, let's go further, past the billion-year mark, past the structural lifetime of any artifact you could build, past the timescale of cometary delivery and orbital evolution, past the point where anything recognizable as the solar system we inhabit today still exists, because the Sun has a clock too, and that clock is running. The Sun is a main sequence star, a yellow dwarf, technically a G-type star, burning hydrogen in its core through nuclear fusion. It is approximately 4.6 billion years old, and it has been in this stable, hydrogen-burning phase for that entire time. The Sun's total main sequence lifetime, the time it will spend in its current state reliably producing energy through hydrogen fusion, is estimated at about 10 billion years, which means the Sun is roughly halfway through its stable life. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core. The core will begin to contract under its own gravity, heating up, while the outer layers of the Sun expand dramatically in response. The Sun will become a red giant, a vast, distended star that, at its maximum expansion, will likely extend to somewhere around the current orbit of Earth, or perhaps slightly beyond. During this expansion, the inner solar system will be transformed. Mercury will almost certainly be engulfed. Venus will be engulfed or severely altered. Earth's fate is debated. Some models suggest it will be engulfed by the expanding red giant. Others suggest it will spiral outward as the Sun loses mass during the red giant phase, potentially escaping engulfment. Either way, Earth's oceans will boil away billions of years before the red giant maximum as the increasing luminosity of the aging sun drives a runaway greenhouse effect. The surface of Earth will be sterilized of complex life roughly 1 to 2 billion years from now, as the sun's luminosity continues to gradually increase, a process that has been ongoing throughout Earth's history. But out in the Kuiper Belt, at 40 astronomical units, when the sun becomes a red giant, the habitable zone and the region around a star where liquid water could exist on a planetary surface moves outward dramatically. Calculations suggest that during the red giant phase, the habitable zone of the sun might extend to roughly 20 to 30 astronomical units. The Kuiper Belt at 30 to 50 astronomical units would find itself in or near this expanded habitable zone for the first time in the solar system's history. The icy surfaces of Kuiper Belt objects would begin to sublime at rates far exceeding anything they experience today. Water ice, which is stable at current Kuiper Belt temperatures, would begin to melt on the surfaces of large Kuiper Belt objects. Nitrogen and methane ices would sublime more rapidly. For a period estimated at perhaps 1 to 2 billion years, the duration of the red giant phase, the outer solar system would experience a brief, dramatic warming. Brief, in astronomical terms, 1 to 2 billion years. During this period, the frozen material in the Kuiper Belt, including whatever atomic remnants were once part of you and your habitat, would be mobilized, melted, sublimated, incorporated into the geologically active surfaces of objects that have been frozen since the beginning of the solar system. If any of the larger Kuiper Belt objects, Pluto, Eris, Makemake, develop liquid water oceans during this period, even transiently, the chemistry possible in those environments could be extraordinary. We know from studies of Europa, Enceladus, and the subsurface oceans of other icy moons that liquid water in contact with rock, heated by tidal or radiogenic energy, can produce chemical environments capable of supporting life. A transiently warmed Kuiper Belt object briefly hosting liquid water on its surface would represent a new window of possibility in the outer solar system, a window opening 5 billion years from now. A window that exists because the sun is dying. Your atoms, if they were incorporated into a Kuiper Belt object, rather than dispersed as cometary dust, might be present in that window, might be part of whatever chemistry unfolds on the surface of a briefly warm Pluto 5 billion years from now. The thought experiment has now travelled from 4 seconds, the useful consciousness window in vacuum, to 5 billion years. That is the span of Phase 3, the geological and astronomical phase, the phase in which the question of survival has been completely left behind, replaced by the question of persistence. What persists of you, and for how long, and in what form? The honest answer is your atoms persist essentially forever, on any time scale that is meaningful to discuss. The organization of those atoms, the structure, the information, the pattern that made you specifically you, persists for a few years at most in the biological sense, and for millions of years in the frozen chemical sense. But the timescales are not done yet. We are still in the age of stars. We are still in an era when the sun burns, when planets exist, when the solar system has the basic structure it had when you were alive. Everything we have talked about so far, the oxygen window, the habitat extension, the cryogenic preservation, the radiolytic chemistry, the red giant transformation, all of it happens while the universe is still, broadly speaking, recognizable. Beyond the red giant phase, beyond the 10 billion year mark, beyond the white dwarf remnant that the sun will eventually become, lies something else entirely, a universe that is not recognizable, a universe that is running a different set of clocks on a different set of timescales toward an end state that is as close to nothing as physics allows. The countdown to that end state is the longest clock in this video. And it has been ticking since the beginning of time. The sun dies in 5 billion years. That sentence is worth sitting with for a moment before we move past it, because it is easy to hear a number like 5 billion years and let it pass through you without leaving a mark. 5 billion is too large for the human brain to hold as a felt reality. It is a number that exists in the same cognitive category as infinity, technically finite, theoretically graspable, but experientially meaningless, because nothing in the lived human experience scales to it. So let's try to feel it, rather than just count it. The oldest living thing on Earth right now is a bristlecone pine tree in the White Mountains of California, estimated to be approximately 5,000 years old. That tree was alive when the pyramids of Giza were being built. 5 billion years is 1 million times longer than that tree has been alive. If you compressed the entire history of the bristlecone pine, every ring, every drought, every ice storm, every season since before writing existed, into a single second, then 5 billion years would be 11.5 days. The sun will outlast everything we have ever built, everything we have ever thought, every civilization that has ever risen and fallen on this planet by a factor of 1 million, and 5 billion years is not even the beginning of the deep future. It is the end of the beginning. When the sun exhausts its hydrogen fuel and expands into a red giant, the transformation does not happen instantaneously. It is a process, unfolding over hundreds of millions of years as the core contracts, heats, ignites helium fusion, and the outer layers respond to the changing energy budget. At its peak, or the red giant sun will be roughly 200 times its current diameter, so large that if you placed it at the center of our current solar system, its surface would extend beyond the orbit of Venus and perhaps to Earth's current orbital distance. During this phase, the sun will lose mass. The solar wind intensifies dramatically during the red giant phase. Estimates suggest the sun may lose 30 to 40% of its total mass during this period through an enhanced stellar wind. This mass loss is gravitationally significant. As the sun loses mass, its gravitational grip on the planets weakens and the orbital radii of all the planets expand outward. This is one of the mechanisms that might allow Earth to escape engulfment, the expanding orbit keeping pace, or nearly keeping pace, with the expanding stellar surface. After roughly 1 to 2 billion years as a red giant, the sun will exhaust its helium fuel. The outer layers will be expelled in a beautiful, slow explosion, a planetary nebula expanding outward at tens of kilometers per second, not a supernova. The sun is not massive enough for that, a gentler exhalation, a breath. The expelled gas will glow as it is ionized by ultraviolet radiation from the hot remnant core. And at the center of that expanding nebula, a white dwarf. A white dwarf is the compressed remnant of a star's core, a sphere roughly the size of Earth, but containing roughly half the sun's remaining mass. The material in a white dwarf is in a state called electron-degenerate matter. Electrons and atomic nuclei packed so tightly together that quantum mechanical effects prevent further compression. Oh, the white dwarf is not powered by fusion. It has no fuel left. It simply radiates its residual heat into space, slowly cooling over billions of years. The sun's white dwarf remnant will form approximately 7 to 8 billion years from now. It will begin at a surface temperature of roughly 100,000 Kelvin, far hotter than the current Sun's surface, and it will cool steadily over tens of billions of years as it radiates that heat away. In the context of your atoms in the Kuiper Belt, or whatever the Kuiper Belt has become by this point, which is a question worth dwelling on, the formation of the white dwarf represents a dramatic shift in the thermal environment of the outer solar system. The planetary nebula phase would briefly illuminate and heat the entire outer solar system. The expanding gas shell, glowing in UV and visible light, would pass through the Kuiper Belt region. For a period of perhaps tens of thousands of years, the outer solar system would be warmer and more energetically active than it has ever been. Then the nebula dissipates. The white dwarf sits in the center, cooling. The outer solar system settles into a new thermal equilibrium, colder than it is today, because the white dwarf, even though it is hotter than the current Sun's surface, is far smaller and therefore radiates far less total energy. The luminosity of the white dwarf is initially higher than the Sun's, but drops rapidly as it cools. Within a few 100 million years of formation, the white dwarf's luminosity will have fallen below the Sun's current luminosity and will continue falling. Eventually, on a timescale of many tens of billions of years, the white dwarf cools to temperatures comparable to its surroundings. At that point, it becomes a black dwarf, a cold, dark, inert sphere of electron-degenerate matter, effectively invisible against the background of space. The problem for anyone trying to work out these timescales is that no black dwarfs yet exist in the observable universe. The universe is approximately 13.8 billion years old, and the cooling time required to produce a black dwarf from even the oldest white dwarfs is estimated at somewhere between 1 quadrillion and 1 quintillion years, 10 to the power of 15, or 10 to the power of 18 years. The universe is not yet old enough by a factor of roughly 100 million to have produced its first black dwarf. We are in the present moment. I'm in the very early universe, not in terms of the Big Bang. 13.8 billion years sounds ancient, but in terms of the full span of time the universe will experience before it reaches its coldest and most inert states, we are in the first fraction of a percent of cosmic time. Let that sit for a moment. Everything that has ever happened, the formation of the first stars, the birth and death of hundreds of generations of stars, the formation of Earth, the entire history of life, every civilization, every thought, every moment, all of it has occurred within the first tiny fraction of the universe's potential lifespan. The universe is not old, it is young. We are witnessing its early morning. Now let's talk about what comes after the stars, the current era of the universe, the one we inhabit. The one that has persisted for the last 13.8 billion years is called the Stelliferous Era by cosmologists. Stelliferous means star-bearing. This is the era when hydrogen gas collapses under gravity to form stars. Stars burn their fuel and die, and the remnants of old stars seed the next generation. It is the era of light, of nuclear fire, of the complex chemistry that stellar nucleosynthesis makes possible. The Stelliferous Era will end, not with a bang, with a gradual dimming. The raw material for new stars is hydrogen gas. The universe began with an enormous reservoir of hydrogen. Roughly 75% of all normal matter by mass was hydrogen at the time of the Big Bang. But that hydrogen is being consumed. Every star that forms converts hydrogen into helium and heavier elements through fusion. When that star dies and expels its material, some of the hydrogen is returned to the interstellar medium, but not all of it. The heavier elements, the carbon, oxygen, silicon, iron, are locked away. The fraction of the universe's mass available for new star formation decreases with every stellar generation. The rate of star formation in the universe has already been declining for billions of years. The peak of star formation in cosmic history occurred roughly 10 billion years ago. Since then, the rate has been falling. Today, the universe forms stars at roughly 1/30th the rate it did at its peak. The last stars will form somewhere around 100 trillion years from now, 10 to the power of 14 years. After that point, all remaining hydrogen will either be locked in stellar remnants, incorporated into planets and other bodies, or so diffusely distributed that gravitational collapse into new stars becomes impossible. The last stars to die will be the smallest, most frugal ones, red dwarf stars. Red dwarfs are the most common type of star in the universe, constituting roughly 70 to 75% of all stars. They burn so slowly that their lifetimes are extraordinary. While the Sun will live for 10 billion years, a typical red dwarf with 1/10 the Sun's mass will live for roughly 10 trillion years, 1,000 times longer than the Sun. The smallest red dwarfs, with masses around 8% of the Sun's mass, barely above the threshold for hydrogen fusion, may live for up to 100 trillion years, 100 trillion years, 10 to the power of 14. During the Stelliferous Era, any atoms from your body that were scattered through the outer solar system would continue their slow orbital evolution. Some would be incorporated into Kuiper Belt objects, some would be swept inward by cometary dynamics, and perhaps absorbed into the Sun's remnant white dwarf or scattered through the inner solar system. Some might be ejected entirely from the solar system. Gravitational three-body interactions occurring on long timescales can give individual objects enough of a velocity kick to exceed solar escape velocity. A small fraction of your atoms over hundreds of millions to billions of years might be lost to interstellar space entirely. The atoms that escape the solar system enter the interstellar medium, the diffuse gas and dust that fills the space between stars. There, they mix with the broader galactic chemical inventory. They drift on timescales of billions of years. They might be incorporated into the next generation of stars formed from collapsing gas clouds, if any such stars form in the vicinity. They might be incorporated into planets around those stars. The carbon that was in your body might become part of a carbon-bearing molecule in a molecular cloud 50 billion years from now, in a region of the galaxy that is slowly contracting toward a new stellar system. You can follow this chain indefinitely, but you reach a fork at some point, because the very long-term fate of matter depends on physics that we do not yet know with certainty. The key question is whether protons decay. In the standard model of particle physics as currently formulated, protons are stable. They do not spontaneously decay. A proton left alone will remain a proton indefinitely. But many extensions to the standard model, grand unified theories that attempt to unify the strong, weak, and electromagnetic forces, predict that protons should decay, with half-lives estimated at somewhere between 10 to the power of 31 and 10 to the power of 36 years. No proton decay has ever been observed. Experiments like the Super Kamiokande detector in Japan have searched for proton decay for decades and found nothing, setting lower bounds on the proton lifetime of greater than 10 to the power of 34 years for the most sensitive decay channels. This means that if protons decay at all, they do so very slowly, but the implication for the very long-term fate of matter is profound. If protons are unstable, even if their half-life is 10 to the power of 36 years, then over sufficiently long timescales, all atomic matter dissolves. Every atom in the universe, including every atom that was ever part of you, eventually ceases to be an atom. The protons that make up the nuclei of carbon, hydrogen, oxygen, nitrogen, every element in the periodic table, would decay into positrons, photons, and neutrinos. On a timescale of roughly 10 to the power of 40 years, assuming a proton lifetime around 10 to the power of 36 years and accounting for the statistical nature of decay, essentially all normal matter in the universe would have decayed not into other matter, into radiation and neutrinos, into forms of energy that do not have the organizational capacity to build atoms, molecules, ductin, or any of the structures that matter makes possible, 10 to the power of 40 years. To compare this to the time scales we have been discussing, the age of the universe is 1.38 times 10 to the power of 10 years. The lifetime of the Sun is 10 to the power of 10 years. The end of the Stelliferous Era is 10 to the power of 14 years. The cooling time for black dwarfs is 10 to the power of 15 to 10 to the power of 18 years. And proton decay, if it occurs, completes on a time scale of 10 to the power of 40 years. Each step is not just a little bigger than the last, each step is many orders of magnitude larger. The jump from 10 to the power of 18 to 10 to the power of 40 is a factor of 100 billion billion. The universe has almost incomprehensibly more time ahead of it, even after the last black dwarfs have formed, than has elapsed since the Big Bang. But before we reach proton decay, and we need to address the most dramatic event in the deep future, the one that the physics between the Stelliferous Era and proton decay is dominated by: black holes. After the Stelliferous Era ends, after the last red dwarf burns out around 10 to the power of 14 years, the universe enters what cosmologists call the degenerate era. This is the age of stellar remnants, white dwarfs cooling toward black dwarfs, neutron stars spinning down their rotation, brown dwarfs drifting in the dark. It is an era of cold, inert objects, mostly dark, mostly silent. But it is not a static era. On very long timescales, two processes continue to operate. The first is gravitational dynamics in galaxies. Galaxies are not rigid structures. They are dynamic systems in which the gravitational interactions between individual stars and objects cause slow energy exchanges over time. Through a process called two-body relaxation, objects in a galaxy gradually exchange energy. Some objects receive enough energy to be ejected from the galaxy entirely, while others lose energy and sink toward the galactic center. Over time scales of 10 to the power of 19 to 10 to the power of 20 years, this process causes essentially all the stellar remnants in a galaxy to either be ejected into intergalactic space or spiral into the central supermassive black hole. The black holes then dominate. Black holes, as understood through Stephen Hawking's theoretical work in the 1970s, are not truly permanent. They evaporate. Through a quantum mechanical process, pairs of virtual particles are spontaneously created near the event horizon of a black hole. One particle falls in, the other escapes, and the net effect is that the black hole loses mass at an extraordinarily slow rate. Slower for larger black holes, faster for smaller ones. This process is called Hawking radiation. The evaporation timescale for a black hole scales with the cube of its mass. A small black hole, say one with the mass of our Sun, would evaporate in roughly 2 times 10 to the power of 67 years. But the supermassive black holes at the centers of galaxies with masses millions to billions of times the Sun's mass take vastly longer. The supermassive black hole at the center of our galaxy, Sagittarius A star, with a mass of roughly 4 million solar masses, it would take approximately 8 times 10 to the power of 89 years to evaporate via Hawking radiation. 10 to the power of 89 years. Long before that, around 10 to the power of 40 years, if proton decay occurs, all the normal matter in the universe will have decayed. The only things left will be black holes and the radiation and leptons produced by proton decay. And then, after another incomprehensible span of time, the black holes evaporate. When the last supermassive black hole evaporates, it releases its mass energy as a burst of high-energy photons and particles. A final flash of radiation emitted by the last organized structure in the universe, and then nothing. After that, the universe is in a state called heat death, maximum entropy, a thin, cold, dark, expanding sea of photons and neutrinos and other elementary particles, all at essentially the same unimaginably low temperature, with no organized structures, no energy gradients, no way for any physical process to do work. The thermodynamic concept of heat death was first articulated by Lord Kelvin in the 1850s, drawing on Carnot's work on thermodynamic cycles and the second law of thermodynamics. The second law states that in a closed system, entropy, the measure of disorder, tends to increase over time. In an isolated system, organized structures spontaneously dissolve toward disorder, and the universe, as the largest system we have access to, is subject to this law on the grandest possible scale. The heat death is not a violent end, it is a whisper rather than a bang. The last photon from the last evaporating black hole spreads through an expanding universe, its wavelength stretched by cosmic expansion until its energy approaches zero. The last neutrino coasts through empty space, effectively alone in a universe too cold and too diffuse to interact with anything. And then, as far as physics can currently tell, nothing changes anymore. Not because time stops, but because there is nothing left that can change. No energy gradients, no organized structures, no processes, just the cold and the dark and the expanding nothing. Now connect this to where we began. You were stranded beyond Neptune. The immediate oxygen crisis gave you 4 to 7 hours. The extended habitat scenario gave you 3 to 5 years. Cryogenic preservation gave your physical remains millions of years of chemical stability before radiolysis began to alter the molecular signature. The red giant phase, like 5 billion years from now, briefly warmed the Kuiper Belt. The Stelliferous Era ended at 10 to the power of 14 years. Black dwarfs cooled at 10 to the power of 15 to 18. Proton decay completed at 10 to the power of 40. The last black hole evaporated at 10 to the power of 89 to 92. Look at this sequence. Really look at it. The gap between 4 hours and 5 years is a factor of roughly 10,000. The gap between 5 years and 1,000,000 years is a factor of 200,000. The gap between 1,000,000 years and 5 billion is a factor of 5,000. The gap between 5 billion and 10 to the power of 14 is a factor of roughly 20,000. The gap between 10 to the power of 14 and 10 to the power of 40 is a factor of 10 to the power of 26. Each successive gap is larger than all the gaps before it combined, and then some. The timeline does not just extend, it explodes outward in a way that makes the earlier timescales look like rounding errors. Your 4 to 7 hour survival window, measured against the full span of cosmic time from the stranding to the last evaporating black hole, is an incomprehensibly small fraction of the total. If you stretch the full cosmic timeline from the moment of your stranding to heat death across the distance from Earth to the Sun, 150 million kilometers, your survival window would be represented by a distance of approximately the width of a single atom. One atom's width out of 150 million kilometers. That is how significant your survival was in the context of what comes after. And yet, the fact that you were there at all, the fact that a thing made of atoms organized itself into a structure complex enough to ask how long it would survive, is itself one of the most extraordinary events in the known history of the universe. Not because it was important to the universe does not register importance, but because the conditions required to produce a thing that can ask questions, that can measure time, that can feel dread at the dark beyond Neptune, those conditions are extraordinarily specific, extraordinarily fragile, and extraordinarily brief. The universe will spend 10 to the power of 89 years in a state that cannot produce anything like you. A few billion years, a tiny, early, well-lit window, is the only time when stars burn and planets form and chemistry is complex enough and energy gradients are steep enough to support the kind of organized information processing that constitutes a mind. You existed in that window, barely, briefly, at the edge of the solar system with 4 hours of air, but you existed. Let's come back. Not because the deep future is done, it isn't, and the clocks we described in the last section will run whether we watch them or not. But because the point of following those clocks all the way to heat death was never to lose the human being in the abstraction. It was to bring the human being back from that distance with something changed, with a different sense of scale, with a different relationship to the 4 to 7 hour window that started all of this. So let's come back to the suit, to the cold, to the single bright star where the sun used to be. You are stranded beyond Neptune. It is, for our purposes, right now. Not a hypothetical future, not a thought experiment happening at a safe remove. Right now, in this moment, the physics applies. The suit is running. The CO2 is building. The temperature is dropping at the rate that the thermal calculations say it should. The signal lag to Earth is 5.5 hours in each direction, which means any distress call you send will arrive at Earth after your life support has already failed. You have, at best, 7 hours, at worst, 4. Most likely, somewhere in between, depending on your metabolic rate, your stress response, the initial charge state of the suit's batteries, on the specific thermal environment of your exact location in the Kuiper Belt, and a dozen other variables that real engineering would need to account for. This is the baseline. This is the floor. Everything we have explored in the last 4 parts of this video was built on top of this floor, extending the thought experiment outward through technology, and then through physics, and then through cosmology, until we reached a state of absolute thermal equilibrium that is, for all practical purposes, the end of time. But the floor is still there. The 4 hours is still there. And it is worth spending some time with what those 4 hours would actually be like, not just physiologically, we covered that in detail, but experientially, phenomenologically, what it would feel like to be conscious in that place, at that time. with that knowledge. Because this channel's purpose is not just to inform, it is to create the kind of quiet, contemplative wait that comes from truly reckoning with something real. And there is nothing more real than the specific texture of a moment at the edge of everything. The first thing you would notice is the silence. Not the silence of a quiet room where there is always some ambient sound, the hum of electronics, the distant traffic, the involuntary sounds of other people existing nearby. The silence of the outer solar system is total, in a way that no environment on Earth can replicate. In a vacuum, there is no medium for sound waves to propagate. Inside your suit, you can hear your own breathing, your heartbeat, the mechanical sounds of the life support systems cycling. These sounds are close and intimate, contained within the small pressurized bubble of air around your body. Beyond the suit wall, nothing. The silence is not an absence you notice gradually. It is a presence. It pushes back. The second thing you would notice is the stars, and this is where the experience diverges most sharply from anything you might have imagined. The stars beyond Neptune are not like the stars seen from Earth. On Earth, even on the clearest night in the most remote location, you are looking at the stars through a column of atmosphere that scatters light, introduces turbulence, and limits the effective darkness of the sky. The sky between the stars on Earth is not truly black. It is a deep blue-grey, lit by airglow, by light pollution even in remote areas, by moonlight, by the faint luminosity of the atmosphere itself. In the outer solar system, in the vacuum, there is no atmosphere. The sky between the stars is genuinely, absolutely black. Not dark, not dim, black. The absence of any photon in those directions, and the stars themselves, without atmospheric turbulence to blur them, do not twinkle. They are points, geometrically precise, unwavering points of light against an absolute black ground. You can see more of them. The limiting magnitude in vacuum with dark, adapted eyes extends significantly beyond what is possible on Earth. Estimates suggest that in the vacuum of space, away from any nearby bright objects, the human eye might resolve stars down to magnitude 8 or 8.5, compared to roughly magnitude 6 to 6.5 from Earth's surface under ideal conditions. The number of visible stars roughly doubles. The Milky Way, which from a dark Earth location appears as a soft band of light, resolves into a more detailed structure, the individual bright regions, the dark dust lanes, the core, and the Sun, your Sun, the star that warmed the planet you came from, the star around which you have orbited your entire life without ever thinking of it as something you could lose, is a point. Magnitude negative 16.7, roughly, which makes it by far the brightest star in the sky. You cannot look directly at it without eye protection, even from this distance, but it is unambiguously a star, not a disk, not the warm, diffuse presence you grew up under, a point of light, bright and cold and small. That specific visual experience of the Sun as a star is one that no human being has ever had. Every human who has ever lived has experienced the Sun as a disk, as a presence, as the thing that defines the daytime sky. The first person who sees the Sun as a star will be experiencing something entirely new in the history of human consciousness. A relationship with the Sun that our entire psychology, our entire mythology, our entire biology evolved under the assumption of never having. And you are having it in the last few hours of your life. The isolation psychology literature, which we discussed in Part 2, consistently notes that extreme environments tend to produce two psychological responses that exist in tension with each other. The first is terror, acute, physiological, the body's alarm system responding to the reality of the situation. The second is a kind of clarity, a stripping away of the ambient noise of ordinary life that leaves the essential things unusually visible. People who have survived extreme situations, shipwrecks, mountain disasters, solo ocean crossings gone wrong, often describe a paradoxical vividness to their experience during the crisis. Not euphoria, not denial, a quality of presence, of being exactly where they are that they describe as unlike anything in ordinary life. The urgency of the situation eliminates the background chatter that normally occupies the mind. There is no room for worry about the future or regret about the past because the present is all-consuming. Whether this would be true in a situation where rescue is genuinely impossible is harder to say. The psychological literature on survivorship is biased toward people who survived, people who maintained some rational framework for their situation, who could construct a narrative in which their actions mattered. In your scenario, the rational framework for survival breaks down fairly quickly when you work through the physics. The signal delay makes rescue impossible. The life support window is fixed. There is no action you can take that meaningfully changes the outcome. What does a mind do with that? We don't know. With certainty. No human being has been in that exact situation and returned to tell us about it. But we have some data points, accounts from people who believed they were about to die, and in plane crashes, in medical emergencies, in extreme sports accidents, consistently describe a particular quality of thought. Thoughts become simple. Relationships feel suddenly primary, abstract concerns, money, status, the accumulated anxieties of a normal life drop away entirely. What remains is the bare structure of a human consciousness, the people it loves, the experiences that mattered most to it, the small sensory details of the immediate moment. If this is true of a person who has a few seconds of belief that they are about to die and then survives, what would be true of a person who has several hours of certainty that they are not going to survive? There is a thought experiment within the thought experiment here. One of the things the isolation psychology research tells us is that the mind, deprived of external stimulation, turns inward and begins to process the content of its own memory and imagination with unusual intensity. In the quiet, in the dark, with the stars unwavering around you and the life support system counting down, the mind would travel. It would go back to everything that preceded this moment, every choice, every relationship, every ordinary Tuesday morning that was just an ordinary Tuesday morning and is now, from this vantage point, something extraordinary simply because it was warm and populated and alive. The Kuiper Belt is, in a sense, the best possible place to understand what Earth is, because from here, Earth is not a place you can go to. It is not the background assumption of your existence. It is a concept, a memory, a point of light, somewhere in the direction of the inner solar system, indistinguishable to the naked eye from the other stars in that part of the sky. Earth is, from the Kuiper Belt, a pale blue dot, a phrase made famous by Carl Sagan when the Voyager 1 spacecraft turned its camera back toward the inner solar system in 1990 and photographed Earth at a distance of roughly 6 billion kilometers. At 40 astronomical units, 6 billion kilometers is about 40 astronomical units, Earth would appear as a faint speck of light in the glare of the sun. possibly not even separately resolvable from the sun itself without optical instruments, smaller than small, a suggestion rather than a thing. Sagan wrote about that photograph with an eloquence that has not been surpassed in the decades since. He wrote about how every human being who ever lived, every king and peasant, every moment of love and cruelty and ambition and tenderness in the history of our species happened on that dot, on that mote of dust suspended in a sunbeam. From the Kuiper Belt, in your final hours, that eloquence is not abstract. It is your actual visual experience. Everything you have ever known, every person you have ever loved, every meal you have ever eaten, every morning you have ever woken up to. It is in the direction of that smear of light near the sun. It is not reachable. It is not even visible as a distinct object without a telescope, and it is going about its business without you. Earth does not know you are here, not in any meaningful, immediate sense. The distress signal you sent 5 hours ago is still travelling toward it at the speed of light and will arrive around the time your life support fails. The people on Earth who might care about you are living in their normal time, in their normal gravity, under their normal sky, with no experiential connection to what you are experiencing right now. The information lag, that 11-hour round-trip communication delay, means that you are genuinely, physically isolated from the rest of your species in a way that no shipwreck survivor, no prisoner of war, no castaway in the history of human isolation has ever been. Historical isolation was always bounded by the possibility of return. The sailor adrift on a raft could see a horizon that ships crossed. The prisoner in solitary confinement could hear the sounds of the prison around them. The explorer trapped by winter in the polar regions knew that spring would come. The connection to the rest of humanity, however attenuated, was always real. In the Kuiper Belt, the connection is severed by physics, not by circumstances that might change, but by the speed of light and the inverse square law and the size of the solar system. You are as isolated as it is possible for a human being to be while remaining within the solar system, and yet you are still within the solar system. You are still, in the gravitational sense, bound to the sun. The atoms of your body were forged in stars that lived and died before the solar system formed, and those atoms found their way into a molecular cloud that collapsed to form the sun and the planets, and eventually you. You are made of the solar system. You are a local phenomenon, a temporary organization of material that originated here and will, over the timescales we have described, remain here, dispersed and altered and incorporated into other structures, but here. The Kuiper Belt is not alien territory. It is the outer edge of home. Note if this is one of the things that the deep time perspective, the billions and trillions of years we travelled through in the last section, gives you when you bring it back to the human scale. It changes the meaning of the word here. From the perspective of heat death and the last evaporating black holes, the entire solar system is a single location. Earth and Neptune and the Kuiper Belt are all the same place. They are all part of the same small, warm, early universe anomaly, a region of space that, for a brief window of cosmic time, organized itself into something complex and interesting. The distance from Earth to the Kuiper Belt, 40 astronomical units, 6 billion kilometers, the distance that makes rescue impossible and communication a 5-hour delay, is, from the perspective of the galaxy, negligible. The galaxy is 100,000 light-years across. The distance to the Kuiper Belt is 0.00063 light-years, a fraction of the galaxy's diameter. You are not far from home in the cosmic sense. You are essentially at home, just in the backyard where the sun is a star and the cold is absolute and 4 hours is all you have. Now let's take all 5 phases, all the clocks we have been tracking, and lay them side by side one final time. Not to review, but to feel the shape of the whole thing. Phase 1. The immediate biological crisis, 4 to 7 hours of suit life, bounded by oxygen, CO2, temperature, and power. The phase in which the relevant unit of time is hours, in which the human body is the limiting factor, in which consciousness is the thing at stake. And the window for consciousness is embarrassingly small against the backdrop of everything that follows. Phase 2. The extended technological survival, 3 to 5 years with a functional habitat, closed-loop life support, nuclear power, and food supply. The phase in which the relevant unit of time is years, in which the human body continues to degrade through radiation, bone loss, muscle atrophy, cardiovascular deconditioning, and psychological deterioration, even as the immediate survival needs are met. The phase in which technology extends the biological window by a factor of roughly 1,000 and then hits a wall that technology cannot move. Phase 3. The geological and astronomical phase. The phase in which the relevant unit of time is millions to billions of years, in which the body is frozen and preserved by the cold, then slowly altered by radiolytic chemistry, then eventually incorporated into the broader chemical inventory of the outer solar system, in which the sun evolves through its red giant phase, transforms the Kuiper Belt's thermal environment, and eventually leaves behind a cooling white dwarf, in which your atoms continue their orbital journey through a solar system that no longer looks like the one you knew. Phase 4. The deep cosmological phase. The phase in which the relevant units of time are trillions and quadrillions and 10 to the power of 40 years, in which the Stelliferous Era ends, the last stars die, the black dwarfs cool, and proton decay, if it occurs, dissolves the atomic structure of all normal matter, in which the black holes that remain evaporate over incomprehensible timescales, and the universe approaches its final state of maximum entropy. Phase 5. Heat-death. Not really a phase in the dynamic sense because nothing changes anymore. The terminal state, the end of the countdown, 10 to the power of 89 to 92 years, and then the last organized energy structure dissolves, and the universe settles into its final, permanent stillness. 5 phases, 4 hours to 10 to the power of 92 years. The ratio of the longest phase to the shortest is a number so large it cannot be meaningfully expressed in ordinary notation. It is larger than the number of atoms in the observable universe. It is, by any intuitive measure, infinite, though it is not. It is finite. It has a value. Physics can calculate it. And somewhere in that ratio, in the tiny, flickering, embarrassingly brief fraction of cosmic time that is phase 1, is the entire experiential content of being you. Every thought you have ever had, every feeling, every moment of wonder or grief or love or boredom, every conversation, every decision, every dream, all of it fits inside phase 1. All of it is smaller than the margin of error in the calculation of phase 4, and all of it matters more to you, to the people who know you, to the brief and improbable community of conscious things that exists on the third planet during the early Stelliferous Era than the entire rest of the timeline. Because the rest of the timeline is not experienced by anything. This is the thing about the deep future that is easy to miss when you are tracking the clocks and following the physics, the trillions of years of the degenerate era, the 10 to the power of 40 years of proton decay, the 10 to the power of 89 years of black hole evaporation, none of it is witnessed, none of it is felt. There is no consciousness present in those eras to experience their duration. The time passes. In whatever sense time passes in a universe without any observing system to mark it, but it passes for no one. Whereas phase 1, 4 to 7 hours, beyond Neptune in the suit, with the stars unwavering and the sun reduced to a point, is experienced, is felt, is witnessed, is real in the only way that anything is ever real, which is that something is present to perceive it. The universe spends 10 to the power of 92 years arriving at a state of absolute emptiness. It spends a tiny fraction of its earliest moments producing things that can look back at it and wonder. We are in that fraction. You were in that fraction. Indeed, in this thought experiment, 4 hours in the Kuiper Belt is more present, more witnessed, more real in the experiential sense than all the silent billions of years that follow the last black hole's dissolution. This is not a comfortable thought. It is not meant to be. Comfort is not what the dark beyond Neptune offers. What it offers is clarity. The same clarity that the isolation research describes in extreme survivors, the stripping away of the ambient noise, the sudden visibility of what is essential. When you are in the Kuiper Belt with 4 hours of air and the sun is a star and the signal delay makes rescue impossible, the question of what matters has a very clean answer. Not the answer that fills most of the waking hours of a normal life. Not the accumulated anxieties and ambitions and comparisons and minor grievances that make up the texture of ordinary existence. Just this. Just now. Just the unwavering stars and the breathing and the 4 hours and whatever small, warm thought you are holding at the end. People who study near-death experiences, and we should be careful here because the research is complex and the interpretations are contested, consistently report that the experience shifts their relationship to time. Specifically, it makes the present feel more real and more valuable. Not in a motivational poster way, not in a perform your gratitude way, in a quiet, structural way. The present moment becomes the thing rather than the background against which the important things happen. In the Kuiper Belt, with 4 hours of air, the present moment is very definitely the thing. And here is the strange gift of the deep time perspective, the thing that following the clocks all the way to heat death gives you, if you let it work on you properly. The present moment is always the thing. Right now, wherever you are listening to this, the present moment is the only location where experience actually occurs. The past is a memory. The future is a model. The present is the only place where something is actually happening, where the atoms are actually organized in the particular way that constitutes a conscious being having an experience. The Kuiper Belt, with 4 hours of air, makes this impossible to ignore, but it is equally true wherever you are. Equally true in whatever warm and populated and ordinary place you happen to be inhabiting right now. Even with the full atmosphere above you and the gravity of a planet beneath you and the sun crossing the sky in a long, comfortable arc, rather than sitting fixed as a bright point in an absolute black, you are in phase 1. You have always been in phase 1. The difference between you, wherever you are, and a person stranded beyond Neptune with a failing suit is not that you have more time. It is that your phase 1 is longer, and it takes place in more comfortable conditions. And the moment of transition into phase 2, the phase in which the biological clock stops and the geological clock takes over, is not yet visible on your particular horizon. But the clocks are running. They are always running. The radiation dose is accumulating. The bones are bearing load. The heart is beating its finite number of beats. The Stelliferous Era is advancing almost imperceptibly toward its end, and the stars are there. They were there before you existed. They will be there, modified, dying, eventually gone, long after anything that could look at them and wonder has also ceased to exist. The Kuiper Belt is 40 astronomical units away. The sun from there is a star. The cold from there is absolute. And the question, how long would you actually survive stranded beyond Neptune, has an answer that spans from 4 hours to the end of time and passes through every time scale that physics knows how to describe. 4 hours if you have nothing, 3 to 5 years if you have everything we can currently build, millions of years if you count what the cold preserves, billions of years if you count what the atoms remember, trillions of years and beyond if you follow what the physics does to everything, all the way to the last evaporating black hole and the final, permanent, absolute silence of a universe that has exhausted every last gradient of usable energy and arrived at its terminal state, and then nothing. Not darkness. Darkness is a perceptual experience, and there is nothing left to perceive. Not cold. Cold is a property of matter, and matter is gone. Not silence. Silence is the absence of sound, and there is no medium for sound and no ear to hear it. Just the expansion, just the empty geometry of space-time, stretching forever, containing nothing, remembering nothing. That is the longest clock. That is the final answer. But you were there, at the beginning, in the suit, in the cold, with the sun reduced to a point and the stars unwavering, and 4 hours of air and the whole incomprehensible future running silently ahead of you like a river running toward a sea so large it can never be found from where you are standing. You were there. And for 4 hours at least, maybe 7 if the suit was good and the cold was merciful and the mind held steady, you were alive. In the dark, beyond Neptune, at the edge of everything. Alive.